what we do, we model excited state dynamics. You shine light on some material, lots of energy are put in. You want to see what happens with this energy. And you want to steer this energy to productive process like solar cell or photochemistry and avoid energy losses to heat, for example. To do this, we developed methodology which combines real-time TDDFT, we describe electrons quantum mechanically, and the vibrational motions are described classically. And classical evolution of atoms would be molecular dynamics, but because we want to consider transitions between different electronic states, it's a combined evolution of classical atoms and quantum electrons. It's called non-adiabatic molecular dynamics, which just means that in addition to just propagating classical particles on a ground electronic state potential energy surface, we also include excited state potential energy surfaces and transitions between them. So TDDFT started in 1980s, 84, Hardy-Gross, Gross and Kohn. And this kind of technology goes back to maybe 60s when people modeled chemistry in gas phase or maybe on surface. I'm not going to talk too much about it. We have, just a second, now it's not, oh, okay. So we have some software that one of my postdocs who's now faculty developed, and now we try to do this machine learning way, etc. I just want to mention some fundamental interesting questions that you might want to think about. So the first big question is, if you have classical and quantum subsystems and you want equation of motion for those two, how you write an equation of motion? The simplest way is to say you use something like Ehrenfest theorem type logic, where you couple averages of quantum mechanical observables, such as force, to classical variables, such as coordinate. But that methodology called mean field, it's mean field way, it actually has problems. And we try to look at it different ways. So for example, we try to define a quantum classical Lie bracket where you try to combine quantum commutator and the classical Poisson bracket. And one way to try to do this is to introduce two Planck's constants and then take limit of h bar goes to 0 in one of them, because that's how you can go from commutator to Poisson bracket in normal quantum to classical mechanics. But you can try to do this in a combined way. So that's one interesting idea we explored. But second problem is that if you treat atoms classically, you actually miss some important effects. Things like tunneling is always important when you have hydrogen atoms. You also have 0-point energy vibrations that are quite important, even if you have pretty heavy elements, because at low temperature, even vibration of lead atoms could be quantum mechanical. So we developed some methodologies where we have some kind of closure. So people have this kind of techniques where you have high order terms decomposed in products of low order terms for many-body problem in electronic structure or in statistical mechanics, but we did this for dynamics, for quantum dynamics. Also, there's this issue of loss of coherence, right? When you have a quantum system coupled to quantum bass, there's one example which is called quantum Zeno effect. If you have a two-level system, let's say, and you have an environment that makes a measurement, or you want to see whether or not your two-level system made a transition, if you keep making the measurement all the time, it's never going to make a transition. And this is known as quantum Zeno effect. Because we're interested in computing rates or studying processes in real time, we have to include this kind of effect into consideration, and you cannot do this by treating your vibrations classically. So we looked at methodologies where you have some kind of effective description of quantum bass. So this would be a stochastic Schrödinger equation or Lindblad equation in open system quantum mechanics. Yeah, and then we have lots of implementation, technology problems, and now we are trying to do everything machine learning way, mainly because almost every student in my group want to have some experience to be able to find jobs, not just in academia, but outside. So there are three related topics. So the calculations are the same and the questions are related. So the first one, I want to start with the generic topic about quantum dots, because this is how nanotechnology started, I would say, in the 80s. People were asking what will happen if you make the material semiconductor smaller and smaller. At some point, properties will depend on the size. And the simplest model would be particle in the box model, in which case you have SPD-like states, just like hydrogen atom. And then people started to call quantum dots artificial atoms, and people still use this language, which is a good language when you look at spectroscopy. If you want to see what color your laser pointer is going to emit, depending on the size of the quantum dot, or your screen in a TV, quantum dot TV, the color can be tuned by the size of the quantum dot. This simple model, artificial atom description, works. But for problems that we're interested in solar energy, it's more complicated. So that's why the general question I'm trying to ask, what's the right way to think about quantum dots? Are they truly artificial atoms, or they're more like molecules if you're coming from the chemistry community, or they're more just bulk semiconductors if you're coming from physics community? And this is not just a matter of terminology, because maybe you want to say phonons versus vibrations, but it's a matter of how you think conceptually about those materials. So so how did quantum dot concept came about? In '84, so Akimov, and then in US, Sasha Afros, who actually was at the conference where we met, also Louis Bruce, people here in US, they've considered what will happen to bulk semiconductor if you confine. And in bulk semiconductor, you have electron and hole. They have some natural distance, which is called exciton radius. If your size is smaller than the distance between electron and hole in bulk semiconductor, then the band gap depends on the size. And in the very simple model, you just say, oh, I have electron with some effective mass, and I solve particle in a spherical well model for that particle, electron with some effective mass, and you get energy levels, which would be SPD, just like hydrogen atom. And the smaller the particle, the larger the energy gaps. And this describes spectroscopy of quantum dots very nicely. But we want to do this for solar energy applications or for light emitting applications. In solar energy, you have a whole spectrum of light you want to harvest from red, let's say, to blue, and blue light has more energy than red light. So if your band gap is tuned to absorb red light, then blue light has much more extra energy, and this extra energy is typically lost to heat. And this is why efficiency of a single junction, single material solar cell cannot be more than 32%, because you lose lots of energy to heat. So people are trying to come up with ideas so that all this extra energy, 68% of energy you're losing, maybe it could be used for something more useful. And one idea was to be able to design materials in which you use extra energy to excite a second electron hole pair. So one photon should give you two excitations, two electron hole pairs, which is not easy to achieve. And so this is how we came into this field in 2005 or so. And then we started to think, and if you think of molecules versus bulk semiconductors, inorganic, you realize that properties are quite different, because in a molecule, you can shine light on the molecule in your eye. That's how you see a molecule isomerizes, you break a double bond. So there's very strong electron vibrational interaction. Yeah, but if you shine light on a semiconductor, probably nothing's going to happen on a bulk semiconductor. Also, electron hole interactions in chemistry, you don't even talk about electrons and holes. You have electronic states that are correlated, because electrons and holes are close to each other and Coulomb interactions are very strong. But in bulk semiconductors, electrons and holes are far. The electric constant is large, so there's screening of Coulomb interaction, so the Coulomb interactions are weak. So then if you change, if you remove an atom from a molecule, it's a whole different molecule, very different chemical reactivity. If you remove one atom from some semiconductor, nothing's going to happen, probably. And molecules have discrete energy levels, and semiconductors have continuum of them. So when you take a nanocrystal, is it more like a molecule or a semiconductor, or the simple model of particle in a box actually works? So this is the idea that Victor Klimov in Los Alamos, who also gave a talk at that conference a couple of weeks ago, showed that if you excite, so you have band gap, Eg is the band gap. If you excite at energy at least twice, but actually 3 times more than band gap, you can generate more than one electron hole pair. And then if you go to 5 band gaps, you can go to pretty high efficiency. And when all of this started, so this was 2004, 2005, people competed, and I've seen talks talking about 700% efficiency, 7 electron hole pairs per photon. But turns out these were experiments that had to be reinterpreted later. So maybe a couple of years later, 2008, yeah. So people realized that this very simple model that you could use to talk about spectroscopy emission, it's too simplistic because you have other processes. And then what they've done, they had to reevaluate the external data, which were fine, by considering other possible processes that were involved. And then the efficiencies dropped from 300% or 700% to maybe 100 50% or so. So the argument why quantum dot should be good for this is because in this simple particle in the box picture, if you make the dot smaller and smaller, energy gaps are going to be larger and larger. And therefore, if you excite here, this is your, let's say this is red, and this will be blue photon. If you excite here to relax down by electron vibrational relaxation will be slow because you're off resonance, right? Because you have very low frequency, this is cadmium selenide or lead selenide, very low frequency vibrations. And the energy gaps here by particle in the box model would be large. You're off resonance, so it's going to be slow. But again, Viktor Klimov published this paper where he reports electron photon relaxation in quantum dots, and it was the opposite of what people expected. If you make smaller dot, green, let's say, or blue, the relaxation was faster than if you have a larger dot. So totally opposite from what people expected. But then eventually, they did find this so-called phonon bottleneck that people are looking at many applications in my field, where you can have nanosecond relaxation of electron. So you have S and P-like states of electron. You do have those states, but in experiment, they had to separate the hole away. And that's because electrons and holes interact. So the picture that people had initially to come up with this whole idea of multiple extons had to be changed, because in reality, you have many, many states. And that's what any atomistic calculation shows. And that's what we showed clearly, is that when you have, even if you have 100 atoms, each atom has 4 valence electrons. So you have 400 valence electrons that can be excited, let's say, into 400 excited states. So you have 400 squared excitations. So the densities of states are very high. You have SPD envelope functions that give you spectroscopy, give you these peaks from SPD-like states, but under each peak, you have many, many excitations. And then because of that, there's no phonon bottleneck. If you excite at energy that is twice bandgap or 3 times bandgap, you have high density of states, and then relaxation is very fast. So this whole concept actually did not quite work. Talked about that. But people still saw this multiple exon generation, although efficiency was not 500%, but still, even if you have maybe 50% efficient process like that, you can increase the solar cell from 32% to maybe 36% or something like that, which would be a very important development, because in the solar cell field, every time they increase efficiency by 1%, they have 5 science papers or something like that. So, and you need to beat silicon, right? And perovskite, which is the last topic I will cover, already is better than silicon solar cell, and only in this case they could now argue that we're gonna make perovskite solar cells. So it's really important, even if you increase efficiency by 1%. So how can you make this happen? In fact, it should happen by purely simple statistical arguments. So if you have a quantum dot, and this is a small one, but the argument remains the same, you have single excited states. So this is a density of single extons. At low energy, you only have single extons, 1 electron hole pair. But at high energy, you can create multiple extons. So if you look at double extons, 2 electron hole pairs, as you increase the energy, the number of ways you can excite 2 electrons versus 1 is much larger. So there's a crossover in the density of states. So if you excite, so if your bandgap is 3 eV in this case, and you excited 6 eV or better 7 eV, so you have to go maybe 2.5 above the bandgap, 2.5 bandgaps. You're gonna create single exton, and then if you have Coulomb interaction that allows you to exchange energy between particles, then you're gonna go from low density of single extons to high density of double exton states by Coulomb interaction. And then what will happen eventually, you're gonna start losing energy to heat, to vibrations. So you start at 7 eV, you go from single exton to double exton, then you lose energy to heat, maybe within 10 picoseconds or so. Eventually you go to this region below the crossover, and then you go back to single extons. So you can still have multiple extons, but you have maybe 10 picoseconds or a few picoseconds to extract charges before they relax and go back to single exton. And then there's also another possibility, which is what you think of in terms of chemistry. So in the physics, you have band structure, and that's your initial description. You have single excitation, and then you have what's called impact ionization. You have charges moving, and when they move, they collide, and there's a channel that gives you another charge excitation. But in molecules, everything is coupled very strongly, and double excited state actually is very strongly coupled and mixes with single excited state. So in small clusters, you can actually excite biexciton that has maybe 5% mixture of single exciton. What we showed is that in small clusters, you immediately get excited states that have double excited character. The intensity of that excitation is low by optical selection rules, but still it's sufficient so that at high enough energy, you immediately generate double excited states, and maybe this way you can increase efficiencies of solar cells. Yeah, what was needed to interpret the initial experiments was to consider other situations. So quantum dots, they have defects. You can have charges trapped. So very often you have some charge that's remaining, like in this structure that I showed you. There's a hole on the surface, there's a ligand on the surface or some shell. So the positive charge is trapped on the surface and you have extra electron remaining. And when you have extra electron remaining, you have new states. And the key states to interpret the experiments were trion states, in which case you have one charge in conduction band and you have a second charge excited across the conduction band. And again, purely statistically, in the relevant energy range, this is the dominant number of states. This is the dominant density of states. To create two excitations, which is what you need for solar cell, you need two positive to negative charges. The number of states of this type is less than the number of states of this type in the relevant energy range. And that's why they had to reinterpret the experiments to allow for these states to be considered. And then they explained the data very well. So what we learned from all of this is that quantum dots, in fact, all nanoscale materials, they're not very clean. If you work with molecules, they're very well defined. And maybe if you make a quantum dots epitaxial in vacuum, they're also very well defined. But if you make all those materials the chemistry way, which I'm a chemist, they're very dirty, not very well defined. And the simple model, such as particle in a box model that started nanotechnology, I would say, it's too simplistic. So what we also learned in collaboration with Todd Krauss in Rochester is that the surfaces of quantum dots, they're not stoichiometric. And so so this is experimental data. He reports absorption, which is black line, and emission, which is red line. And he makes this in solution, so they're very cheap to make. And that's the main motivation, actually, to study materials that I'm discussing, because they're much cheaper to make than silicon, let's say, because silicon, you use vacuum, etc. But this is all solution chemistry, like cooking. Somebody told me at this conference too that if I know how to make tea, I can make a perovskite solar cell. So presumably it's very, very simple. And so what he does, he mixes two chemicals. One has cadmium, one has sulfur. And then he stops the growth. He heats it up, the crystal grows, and then he cools it down, it stops. And then he measures the spectra. So first thing he measures, interesting, is that you have this new line. So you have the first peak, the main peak that follows from particle in the box, but he has a very big feature that does not follow from the simple model. And this is from some trap states, mid-gap trap states. But what was really exciting is that, or surprising, I would say, is that if he puts extra sulfur on the surface, he just adds sulfur, the chemical that has sulfur, he totally kills luminescence. And then he continues, puts cadmium, luminescence appears again, puts sulfur, luminescence disappears. And he can do it many times. Why? So that's what we explained. When you have sulfur, you don't have any emission because you have many trap states. So sulfur needs to make covalent bonds. And when you have some random number of sulfurs on the surface, you don't have the opportunity to make all the bonds that sulfur needs. And therefore, you have many unsaturated bonds, and those bonds create trap states in the gap. If you have cadmium, cadmium has d electrons, more spherical, metallic bonds. You still have trap states, but healing, so it still makes some bonds that make a cluster. So you have a subband of defect states, and there's still some gap remaining. So instead of continuum of many, many trap states all the way across, you have some smaller gap and a subband. And because of this, you see emission from this subband, and the lifetime of excited state is long because you still have a gap across which it takes a long time to relax. So this is collaboration with the Tim Lian, who is now editor-in-chief of Journal of Chemical Physics, by the way. So what he studied in this case was extraction. So there's a quantum dot that has energy levels, and he puts a molecule, and he wants to extract charge. He excites the quantum dot, extracts charge. And in chemistry, this famous Marcus theory Rudy Marcus, he's in Caltech, who got Nobel Prize in the 80s for the model he developed in the 50s or 60s, which is a very simple model, but also gave you some interesting counterintuitive result. So it's a model for a rate. So you have initial state and final state. You want to charge transfer from here to here. And in the model, he studies how the rate depends on the energy gap. And your everyday intuition tells you if your initial and final states have a larger gap, if you go downhill, it's going to go faster. And the rate initially increases as you increase the gap, but eventually it's a turnover. And the logic is very simple. If you have one vibration and two electronic states modeled like this, you have a vibrational motion that brings you to a barrier. But if your final state becomes lower and lower, the barrier becomes smaller and smaller. Eventually, there's no barrier if your final state vibrational parabola is sufficiently low. But if you bring it too low, then the barrier shows up on the opposite side. They cross on the opposite side. So two parabolas, if you move the final state, the product up and down, you decrease the barrier, but then if it's too low, you have a barrier on the opposite side. So, and that's why you have this inverted regime if the energy gap is too low. But in this case, they didn't see this, which again, after the fact is quite straightforward because again, you have to consider the whole. In the model that people used initially, they just said initial state, final state, Marcus theory, you should have inverted regime. But in nanoscale systems, you have a fairly interesting combination of two properties where you have high density of states and also strong Coulomb interactions. In molecules, you have strong interactions between charges, but states are few. In bulk semiconductor, you have many, many states, but Coulomb interactions are screened. But in nanoscale materials, you have both. So what happens, just like for multiple electrons, you have Coulomb interaction, and you have energy exchange between electron and hole. So when the electron loses energy, all the energy goes to the hole. But then very fast, within 3 picoseconds, the hole relaxes by giving energy to vibrations. And after 3 picoseconds, you don't even know that the hole was ever excited. But in a time-resolved measurement or in a simulation like we do, you actually can track all of this. And when you track all of this, you explain why there's no Marcus inverted regime, why this rate, fetch rates never goes down, which was kind of important, at least in our community. Yes, okay, so now I'm gonna switch to plasmonic particles. Again, kind of the chemistry way, because plasmons are collective excitations of many, many electrons, right? And usually people argue that to have a plasmon, surface plasmon resonance, you have to have sufficiently large system, which are hard to study by atomistic calculations like we do. But you can still show that after you increase the particle size, for small particle, you have discrete excitations. But when you make a particle larger and larger, you can very well reproduce plasmon band. So you have spectroscopy of a plasmon that has response in some visible region. Yeah, in fact, right, if you go to Europe and look at cathedrals, they have colored glass. The color of glass in European cathedrals comes from particles that had silver and gold particles that absorb light in the visible, which is plasmon resonance. So once people establish that you can actually reproduce and get useful insights into plasmon properties from atomistic calculations, we started to do dynamics. So this is just an example of one single particle state of a metallic cluster in the region of, in the energy of plasmon resonance. So this would be some d electron state, and then this would be p electron state. So once again, you can think of particles as artificial atoms. What's essential for what we study is that these states are localized very far away from the atom, right? So if you look at this projection of the density, so this is bulk state, it's right inside the particle. This is surface state, and this plasmon state, most of the density is away, and it extends maybe 1 angstrom, 1 nanometer. It extends quite far from the particle. So you have maybe 1 nanometer vacuum, but this vacuum is no longer vacuum because you have electron density from plasmon excitation that extends quite far. What's also important is that electron vibrational relaxation is very slow. Electron phonon interaction is weak because when this density, electron density is away, it doesn't couple to plasmons, to phonons strongly. So this is just showing you peaks, and the height of the peak is the strength of the electron phonon interaction. So for bulk state, it's the largest. Surface state, you have more peaks because you break the symmetry, you have more phonons involved, but for plasmon state, this red peak is very low. So maybe I skip this. in chemistry, people are trying to use plasmons to do photochemistry. And so why plasmons are very important? Because they're very efficient. They interact with light very strongly, right? So claritonics, people use plasmon type excitations for that, for strong light matter interaction. In photocatalysis or photovoltaics, it absorbs sunlight very strongly, so you can expect some efficient process. But people always wonder whether it's some excited state process or it's just heating, because you have a metallic particle. When you have a metallic particle, it's gonna, it has no energy gap, right? And when you have no energy gap, usually within a picosecond or several picoseconds, all the energy, electronic excitation energy goes to heat. And so there's a debate, and this is one journal where people discuss this a lot, whether you truly have excited state photochemistry or you just have very efficient heating, local heating, and then it's just ground state chemistry, but at a high temperature. So what we've done in this case, we developed some machine learning force field, and we showed that you have some, and we see this in many nanoscale materials, you have pretty slow, for our time scales simulations, pretty slow processes. So in this case, it's tens or hundreds of picoseconds. So what happens in this case, you have a top atom of this pyramid, and plasmon is usually localized on sharp parts. So where plasmon excitation is localized, you can have top atom that moves back and forth, and it creates some configuration that could be catalytically active because you have unsaturated chemical bonds there. So it breaks some of the bonds with the main pyramid, and there's an opportunity for that atom to interact with some molecule. And what we also see is that the lifetime of state like this becomes longer. So this is all very fast. But if you think of chemistry, you have some, you want to break CO2, right? You want to store, make CO2 back into methane. You want to break CO bond. So vibration of CO bond, the vibrational period is maybe 50 femtoseconds. So if you can have an excited state that lasts for 10 vibrational periods, there's already a chance that you can break this molecule and maybe start photochemistry. But if you only have maybe 4 vibrational periods, maybe it's not so efficient than if you have 10 vibrational periods. So you have some special states that can be photochemically active. Again, the same question, how can you do photochemistry or photovoltaics if everything should relax to the ground state in a metal? But people still try to make solar cells with metallic particles because they absorb light so well. So the traditional mechanism of what happens is that you have this collective excitation of many electrons, a plasmon. Then there's Landau damping or dephasing, or your collective excitation breaks into independent electron hole excitations, and then charges can inject. But if you have electrons and holes, they should relax by vibrations, energy goes to heat. But what we've shown in 2014 was that when you have a metallic particle on a semiconductor surface that's not chemically happy, you have a 3D semiconductor, and you have a surface that has unsaturated chemical bonds, you can have excited state that has a tail, significant tail, this yellow density, into the semiconductor. So what we showed was that you photoexcite, and when you photoexcite, you have maybe 20% chance that you're going to have electron already inside the semiconductor. And so before I showed you collaboration with Tim Lian, but now we should have collaborated because a year later, he published a science paper where he shows this experimentally. What he shows is the efficiency of charge injections. He monitors charges in the conduction band of a semiconductor, and he excites plasmon resonance, and he tunes the excitation energy. And if you think of a traditional mechanism, you argue that you have electron hole pairs. The excitation energy tells you energy from electron to the hole, but where the electron is relative to the conduction band, it's random. So if you have high excitation energy, it's more likely that the electron will be high enough to be above the conduction band edge, and it can inject. And this is what traditional models predict, some kind of energy dependence of yield of injection on photon energy. But in his experiments, he did not see dependence down to some threshold, which is the energy gap from Fermi level of the metal to the conduction band edge. And he argued that this is indication that you have photoexcited state, that's this charge separated state that we saw in our paper a year before. Yeah, but this only happens, in fact, when you, so in this case, what he did, he grew gold on cadmium selenide, which is another 3D semiconductor. In our calculation, we put gold on TiO2, but if you put metallic particle on 2D material, you see much less of this effect because chemistry is important, because 2D material has a perfect surface. That's why it's layered. And you don't have strong chemical interactions. So if you compare yellow here versus red here, same particle on two different, this is 3D, this is 2D material, the extent of this delocalization of your excited state onto semiconductor is much less. So this is only efficient when you have chemical bonding between the material. Yeah, a couple more. So this is now collaboration with Jihan Lo in Singapore. What he can do, he can measure, he has time resolution, spatial resolution, and force, AFM, some laser, and some microscopy. So what he reports rate of charge transfer from gold that he excites into semiconductor, again, MOS2 to the semiconductor. And he reports the rate as a function of distance. So this material, the gold surface is rough, and he can figure out the distance between gold in a particular spot and MOS2 on top. So he can, and then he measures the rate for different spots. So he can measure rate as a function of distance of gap between gold and MOS2. And he sees this dependence, which according to simple models, it's too weak. If you assume this vacuum between gold and MOS2, the decay should be very fast. But the decay that he sees is not fast. This is, so in chemistry, this is some beta known parameter where you have donor acceptor and a bridge. So this bridge should be a conjugated molecule, basically organic conductor, to get dependence of this matter on the length of your distance, on the length of the bridge. So he sees something as if there is an organic semiconductor between them, but there's nothing. So why? Yeah, but eventually, actually, this becomes sharper. So exactly as I was saying at the beginning of plasmon topic is that you have this plasmon-like state that extends into vacuum quite significantly, maybe by a nanometer or 8 angstroms for sure. This is 8 angstrom. And because of this extension, if you look at the bulk state at low energy, you have no plasmon excitation, you have vacuum. So there's nothing, no overlap between gold and MOS2. But if you have high energy excitation that corresponds to plasmon, you have tails of gold and MOS2 states that overlap. And because of this, you have interesting, efficient charge transfer over large distance. And last topic about metallic systems. So this was collaboration with an engineering group. And it was actually a very interesting experience because, first of all, engineers are really focused on devices. So I learned a lot of devices. And second, because the language is also different, just like I was saying, molecules versus semiconductors. In engineering, what I've experienced is everything is a heat capacity. So electron scattering, electron vibrational scattering, it's all heat capacity. So all the parameters are heat capacity parameters, not electron volts or inverse centimeters. And so what they want to do, for example, they want to make a device which extracts heat one way. So they call it heat diode. So if you have a metal, you have some electronic device that has metal, then you can put a semiconductor, and then you can put another metal. And what happens if you have energetic electrons in this metal, and you have a semiconductor that's intrinsically doped? So you have charge carriers in the conduction band of the semiconductor. Your hot energetic electrons can be transferring energy from metal to the semiconductor. And then if you have another metal on the other side, this energy will go to the second metal and it will never come back because there's energy gap here. So phonon-induced energy transport is not as efficient as electron-induced energy transfer. So you can have energy transfer from only in one direction. So the point of this paper was to figure out how it happens. So there's no longer charge transfer. All the examples I showed you before, it was charge transfer, but this is energy transfer, and it happens by electron-electron scattering at the interface between the metal and the semiconductor. And you have to have already intrinsically doped or doped semiconductor to have charges in that in the conduction band. And we had to develop some additional methodologies because this real-time TD-DFT has very poor scaling with dimensionality. And the last topic is metal halide perovskites, which are very popular materials for the last 10 years, maybe, mainly because they're very efficient. So it took people, I don't know, 50 years to make efficient solar cells, but it took people maybe 5 years only to make efficient solar cells of metal halide perovskites, similar efficiency. And they're very inexpensive to make. It's like making tea. I was told only problem they're not very stable. But maybe people should think of solar cells where you every year you just install a new, you have swappable perovskite or something like that. But from the fundamental point of view, they have very interesting properties, something that you usually don't see in other materials. So I would like to argue that they have features of inorganic matter, they have molecular features, and they also have even liquid-like properties. So first of all, what's the structure? Yeah, maybe this is fine. So this is superposition of maybe 2 picosecond of molecular dynamics snapshots. So you have this red, which is lead. So the material has 3 components. This inorganic lattice. Yeah, so you have lead and iodine. So red is lead and green is iodine. So they're vibrating. And then you have organic molecule in the middle. So this is the molecule. Could be slightly bigger molecule, could be actually cesium, one big inorganic cation. This molecule rotates. So because you have inorganic lattice, it's a good conductor. Because people can make solar cells from organic matter, but usually you can make organic light-emitting diodes efficiently because charges can combine, make exciton and emit. But the opposite process is not very efficient because yeah, Coulomb attractions are strong, the electric constant is weak. So when you photoexcite organic matter, it's hard to separate charges. You lose a lot of extra energy. You lose energy. You need extra energy to separate charges. So if you have inorganic lattice, just like silicon or cadmium selenide, it creates you good conditions for charge separation and also charge transfer. But it has this molecule in the middle that rotates, has dipole moment. So it's almost like a liquid, right? Because when you put a charge in a liquid, ion in a liquid, it creates salvation shells. So the structure of the liquid around the ion changes a lot. So when you have this molecule that can rotate, just like water, if you have positive charge, water rotates oxygen towards cation. If you have anion, hydrogen of water rotates to cation, to anion. So same thing can happen. So in the liquids community, this would be almost, it would be salvation. In the physics community, this would be polaron, but this polaron formation is different from polarons in normal semiconductors, which are very small polarons. This is very large polaron. You have very large scale distortion of your lattice and rearrangement of this molecule inside the lattice. So it's quite different from normal, typical like TiO2 or silicon semiconductors. But the main property of the material is that you don't need to worry about defects too much, right? So lots of technology. Why silicon dominates? Because there's lots of technology to make sure you don't lose charges, so that you avoid, you saturate or passivate defect states, etc. But with these materials, trap states are not bad. And the initial argument was that most of the trap states are very shallow. So for example, the most common type of defect in this material is when you have iodine atom moving. And when it's moving, you can either have extra iodine, which is interstitial, this example, and next example, you have a vacancy. So when you have extra iodine interstitial in the middle where this molecule is, it creates a localized trap state, which is shallow, but not too shallow, because to escape from this trap state back to the valence band for the hole, you need this energy gap is more than kT, almost by an order of magnitude more than kT. So even though it's close to the valence band, but it's not close enough. But in our calculation, we see that when the hole is trapped, it actually gets detrapped much more efficiently than it recombines with the other charge. While in traditional semiconductors, usually you assume that when the charge is trapped, it's gone. After a while, it just recombines with the other charge and it's gone. But in this case, it's not the case. It actually escapes. The one argument was that you have this trap state, which is very localized, and it does not overlap with the other state, with the free charge. So the coupling is very weak because the wave functions don't, the charge densities don't overlap. But turns out that something else is more important, which is the softness of this material. So perovskite is soft. It's almost like organic matter, not quite, but it's much softer than silicon. And because it's soft, you can have a pretty large scale of fluctuations. So this same defect, the interstitial, if you look at the optimized structure, you have some energy for this trap state. But if you do sample dynamics at room temperature, you see huge fluctuation, half an electron volt, even more. And then you cannot even say if this is shallow trap or deep trap. So this whole terminology that people use in inorganic semiconductors, you have shallow traps, deep traps. it doesn't really apply here because the same trap could be shallow or deep depending on time. So you have a whole distribution of energies of the trap state. And this is true of most of the trap states. So this one is deeper, but still there are some times where it's quite shallow and then the charges can escape. So that was, shallow, deep, and dynamics is very important. Now about chemistry. So if you have semiconductor, silicon, you start sending current, structure will not change. If you have inorganic quantum dot, you photoexcite, structure will not change. But if you shine light on the molecule, structure can change. So same can happen here. So if you put a charge, if you have vacancy, right? So now it's a vacancy. In stable state, no extra charge, no light shone, you have no mid-gap trap state. But if you shine light or you send charges and the charges can be trapped, you create new chemical species. What happens in this case, you have two lead atoms and you have iodine, used to be iodine between, and it's missing. So if you replace iodine with electron now, it creates a bond. So before you had positive lead, negative iodine, positive lead was some structure. Now missing iodine, but if you have a charge, this electron in the middle attracts two leads and you make a dimer. And when the distance shortens because of that, you create new chemical species and you have many mid-gap trap states, which can be pretty bad. So if you make solar cell and you characterize it with low light irradiation, you see everything works fine. But if you shine a lot of light, you send many charges, the whole chemistry and changes, mid-gap states appear, and the properties of the solar cell change a lot. You don't have to put charges. These iodines, they vibrate, they migrate. And when they migrate, same thing can happen. So in this case, I'm considering, how do I get rid of that? I don't know. So in this case, I consider migration of vacancy from one location to another location, which happens. And when this happens, the whole structure of perovskite changes and your defect state that is in the band in equilibrium, it actually moves quite deep inside the band gap, and the lifetime of your charge carrier changes by a lot. Same example, but now time scale is much longer. So that's where machine learning is useful. We developed machine learning force field and can sample much longer trajectories. Same lead-lead dimer can form transiently without migration, without charges. Simply, you have a very low acoustic mode, maybe with a period of 50 picoseconds. And every 50 picoseconds, the two LEDs come together. And when they come together, you create a dimer and you have a deep trap state. And this should influence charge carrier dynamics. Now we study grain boundaries. So basically, perovskites are very glassy systems, and they have dynamics on multiple timescales. And structural dynamics that happens on multiple timescales, it influences electron dynamics, also charge carrier dynamics, which influences the efficiencies of solar cells. So when we look at the grain boundary, and we did calculations for a nanosecond, we see some fast component where it slides, and when it slides, some trap states appear for charges. Then you have some fluctuation, nothing really happens. But then half a nanosecond later, some kind of another structural rearrangement happens due to some kind of rotation or angle tilting. And then when that starts, you start seeing many trap states again. So this is not something that you see in silicon or cadmium selenide, but perovskites are very kind of glassy, slow systems where many things can happen. And I'm almost done. I just want to say, another thing. Usually, if you want to have efficient emitters, you cool things down, right? So if you have a molecule, if you cool it down, it emits light for a long time. But if you heat something up, usually electron vibrational relaxation becomes fast and emission is not very efficient. So many things become cleaner, more efficient at low temperature. But perovskites, lifetime of excited state actually becomes longer at high temperature. Why? Because when you photoexcite, you have some disorder, partial disorder due to thermal fluctuations, and charges, electrons and holes, they become partially separated, partially localized and separated. And this matrix element for non-radiative decay becomes smaller because the charge densities of electrons and holes are no longer overlapping. So the temperature dependence of the lifetime actually opposite for perovskites from other materials that people studied before. And we did some machine learning analysis. I'll probably skip this too, because it's perovskite quantum dot. That was the topic of the conference where we met. And perovskite quantum dots basically behave similar, very similar to regular quantum dots. You have Auger processes that I started with, electrons and holes can exchange energy and so on. But to conclude on perovskites, they're very unharmonic materials. So when people make simple models, assuming harmonic vibrations, phonons, these are not phonons. You have very low frequency vibrations, and the system is very unharmonic. So if you raise temperature and you look at the electron vibrational coupling, at low temperature, you have some dominant phonon, but if you increase temperature, you have more and more vibrations contributing to electron vibrational coupling, because the system is very unharmonic. And the types of calculations we do, atomistic calculations, become important, because simple harmonic models that many people use, they don't apply. So I think I'm going to conclude. So what I talked about very briefly about the methodology we developed, which combines real-time TDDFT and non-adiabatic molecular dynamics. So the goal is to model excited state dynamics following light excitation, or if you inject charges, you put a lot of energy, everything happens very fast on femtosecond, maybe not attosecond, but definitely femtosecond, picosecond, nanosecond timescales. And that's why we need these kind of simulations. Everything depends on configuration. There's no approximation about weak coupling, such as people use for perturbation theory, Fermi's golden rule. So that's the value of the simulation. And then I talked about three kinds of systems: quantum dots, which was the beginning of nanotechnology. So spectroscopically speaking, yes, they're artificial atoms. You change the size, you change the energy gap, particle in a box model, SPD states. But in terms of excited state dynamics, they're more like small pieces of bulk, I would say. Because energy is high, density of state is high, Coulomb interactions are screened. Maybe on the surface molecular details matter. But inside the quantum dot, if you passivate the surface well, they're just like small crystals, small pieces of bulk. Plasmonic particles, very interesting. You have special states in plasmons. These states don't couple to vibrations. They extend very far, so they facilitate some charge transport because they extend far. And small atomistic models, they can actually give you some useful insights into real large systems. And metal halide perovskites, very interesting materials. They combine features of inorganic matter, organic matter, and liquids. Very easy to make, very efficient materials in terms of light emission, detection, solar cells. They're just not very stable. Yeah, but chemists have to figure this out, I guess. And so thank you very much for your attention. Thank you.